So let us start the second installment of the seminar. The seminar is quite traditional, but the online version is in its second installment only. So Arya Mazumdar is the speaker today, and I believe most of the attendants know Arya. Arya graduated from UMD. I guess it's 10 years back now, right?
9 years.
9 years, 2011. Yeah, sorry. And after that, Arya has been to a number of places, starting with Minnesota and then moving to University of Massachusetts, which is his current academic home. Arya's initial work had been on error correcting codes, but then he expanded his expertise greatly into all kinds of learning algorithms, applied statistics, and different areas of applied probability and computer science, trace reconstruction, and so forth, and stochastic block models. And today Arya is speaking about learning mixtures. Arya, please, it's all yours.
Yeah, thank you very much. So I have been giving a few seminars in the past few months with the pandemic in the background, but I have never given a whiteboard seminar like this. So I listened to Himanshu's talk. I didn't have the software that he used, but I thought I would just go one step ahead and make it more whiteboard-ish. So I don't have anything written over here now. That doesn't mean that I have not prepared for it at all. So I will try to do everything on the board. There is nothing, you see a blank board, so I will start from there. Hopefully things will go okay. If I get disconnected again, I will try to reconnect, and I will be able to reconnect, I believe. One other thing yes, and so I have some backup slides. So in any time, like if we have time constraint and for some reason we cannot really do this whiteboard thing because it is too slow, we can always switch to slides. Hopefully it will not be that. And then I would like to thank all the organizer, I think Zitan, Shagnik, and Advay. I know Zitan, I don't know. I think Shagnik and Advay is more recent, so I don't know you guys, but thank you very much for inviting me. I have given numerous talks in this seminar, and I think I have learned the most from this seminar as well. So, but the last time I spoke in this seminar is quite some time back. So it is really nice to be back there, even virtually. So what I'm going to talk about is, so let me just. Learning mixtures and trace reconstruction. So whether this orientation is good, I'm not sure, but we will figure out. So this is actually joint project.
If you rotate it till the screen better.
You think this is better?
Yeah, like this.
This is better? Okay, great. So this is a joint work with so all the work that I have been doing in mixture and related fields is with my PhD student. His name is Shomobroto Pal. He is the main driver of this, this work and some other work as well. He's great. He's going to graduate next year and he will be looking for postdoc positions. He wants to be in academia. That's where he wants to make his career. So he will be looking next year. In addition to Shomobroto, this work is also a joint work with Akshay Krishnamurthy. I'm not going to write the full name. Akshay is in Microsoft Research, New York, and also with Andrew McGregor, who is my colleague at UMass Amherst. Okay, so there are two things in the title. One is learning mixture and the second one is trace reconstruction. So I think learning mixtures is something that people know more about. I'm not going to, but let me still give some brief introduction to learning mixtures. And trace reconstruction is what I'm going to spend most of my time in this talk. I think it will be slightly over an hour or around an hour, but feel free to stop me anytime. In that way, I will know that you are listening and not playing online poker or something else. Okay, so what is, so let's just go over one by one. So learning mixture, so this learning over here, this doesn't really refer to machine learning. It basically refers to statistical reconstruction or recovery, right? So in general, when we try to learn a distribution, okay, so we think that this distribution is coming from some class C, and then what we do is we receive samples x1, x2 to say xm. These are the samples that that are from that distribution, and now our job is to learn that distribution, right? So usually we know something more about this C, this class C. We know more about this, and which makes learning more easier, right? So what about learning mixture? This is just a more special case where we know that this this distribution, we know a lot about this class C. We know that it's actually coming, the samples that we are seeing is actually coming from some distribution F1 with probability P1 plus some distribution F2 with probability P2 and so on. So there are k different distributions, and say we know that each of Fi is in some class C. It doesn't have to be the same class, it can again be some different classes. Yeah, right. So that's how we are receiving the samples, and again we know a lot about these CIs, and we basically, for example, we can know that these are all these CIs are, say, Gaussian distribution. Right. So in particular, uniform mixture of Gaussians when P1, P2 up to Pk all are same is extremely well studied. So the literature of mixture basically goes back at least to 1894 to some treatise of Poisson, and it is very popular. There are numerous references. I'm not trying to list a lot here. So mixture of Gaussians are particularly popular because they are often used to prove claims about clustering, and they actually motivate the use of the popular k-means algorithm. Okay, so the results in distribution learning in general and learning mixtures in particular, that can take different forms. So all the results that we can get in the literature. Again, so I'm not going to talk only about my own work here. As a matter of fact, most of the time I'm going to talk about other people's work. I'm going to explain some basic stuff. So I'm not assuming any knowledge. So just bear with me if these things are redundant to you. So the results can be of different flavor. One is, say, parameter estimation. And again, this is not special to mixtures. This basically goes for in general learning distribution. So in parameter estimation, you know that this f is actually f theta, and theta is coming from a set. It can take values from some set. So this is a, for example, Gaussians with unknown mean and variance, and you want to basically learn the mean and variance exactly. So that's parameter estimation. And then there can be density estimation. Okay, I'll try to use the density estimation. So here you are not trying to recover the parameters, but you are just trying to fit a probability distribution. And here again, there can be two types of result when there is, one is called proper learning. That means you know that this mixture or this distribution is coming from some class, and you basically want to recover or want to return a distribution from that class. And then there can also be improper learning. So what is improper learning? You basically just give me a distribution that best fits the data. It doesn't necessarily comes from that class, right? So, and in all of them, there are a lot of prior work. Again, I think the prior works some of them can be found in the references that I have provided, and if you look within them. And what is different about mixtures from general distribution is that they can be multimodal, right? So you can have something like this. And in particular, this type of things are, if you have probability distribution that looks like this. It's hard to sometimes estimate, and we will see why this is, how this is hard. What do we mean by hard? Okay. So why, like in this distribution learning framework, whether the problem is easy or not, it depends on whether we have a good approximation of the variational distance between two. Yeah, so there is a message from Zitan. Yeah, so whether the problem is easy or hard, it depends on a good approximation of the total variation distance between two candidates from the class. So for example, if you just take, so suppose this is the class where the distribution is coming from, and you have two candidates, say F and F prime. They both belong to the class, and F is not equals to F prime, right? So then somehow you need to, I'm just telling this in a statistical sense and not a computational sense. I mean, problems can be hard computationally, but most of the time when I'm speaking in this particular seminar, hard means information theoretically hard. We are not going to bother about how long it takes us to find the solution. We'll be happy if we can find some solution. So we can actually look at the total variation distance, which is half of the L1 distance between two candidate distributions. And so what we want is actually, when we try to recover something, we will see that it's easy if we can get some good lower bounds on this. So for some, if we get a really good lower bound over here, then we can say that the distributions are far apart. Now, not necessarily this has to be in the total variation distance, but total variation distance sort of comes off naturally in most of these learning problems. There are other natural distribution, and if we can show that distributions are apart for in those, then it's sufficient sometimes. So total variation distance is probably most basic, and if you look at the hierarchy of how these distances are placed, like almost all other divergences or distances between distributions are actually their upper bounds on the total variation distance. For example, if you use Pinsker inequality, you will see that this total variation distance is upper bounded by the KL divergence, which is actually sometimes easy to compute and approximate, especially for high dimensional distributions. What happens is we don't really have good lower bounds on the total variation distance. And if we are to recover something, if we are to show that something is learnable, then we want to show that any two candidates from this set are actually far apart, right? So we want lower bounds. And for the multimodal type distributions, it's very difficult to come up with good lower bounds on the total variation distance. Okay, so now you might ask the question, or you might not, you already know this, that why just giving a guarantee that any two candidates from this set being far apart in some distance is a good condition of learnability of those distribution? And the answer is pretty simple, because if they are far, then you can just use something like a minimum distance decoder, right? So you can basically look at all the samples that you have got and try to form an empirical distribution. And then you can go over, again, we are not bothered what happens computationally, you can just go over all the candidates distribution in the set C or the class C and find out whoever has the minimum distance, right? And you can just say, so that's also, sometimes it can be through maximum likelihood decoding. And so in all of this, you just do two steps. So first of all, you see whether you can tell two candidates apart, right? And if they're far in total variation distance, then indeed you can actually tell them apart. And then you use this minimum distance algorithm, and it's pretty straightforward to show that if they're far apart, then you think we'll make this rigorous later in this seminar. then you have basically everything. Then you can learn which distribution the samples are coming from. Okay, so again, the reason of all this is that for mixture of these multimodal distributions, often lower bounding total variation distance is pretty hard. It's harder than, it is already pretty difficult in case of unimodal distributions, unless it is like some very special families of distributions like just Gaussians. But even for pair of Gaussians, there is no good lower bounds on the total variation distance, Gaussian mixtures, right? Okay, so that's my introduction to learning mixtures. Now I'm going to move to something completely different. And by the end of the hour, I'm hoping to come back to mixture and show you how this is relevant to mixture. What I'm going to talk about now is called trace reconstruction. Again, just feel free to ask question. I'm assuming so far things are very basic, so you don't have any question, but yeah, it's really useful to me as well. So what is the trace reconstruction problem? So trace can mean different things, and mathematically it has a very precise meaning. So this is actually a completely different meaning because computer scientists introduced this. So, and it has a lot to do with the binary deletion channel, which is a very notorious channel in information theory. So what is a deletion channel and how does it operate on a binary string? So suppose you have a binary string or vector. So say this is 0, 1, 0, 0, 0, 1, 0, 0, something like this. And what does a deletion channel do? So this is a IID deletion channel. So it just IID deletes with some deletion probability P, right? The IID deletes each bit. And as a result, you have a subsequence or a random subsequence of the original sequence. So what is a random subsequence? So for in this one, you can have something like 0, 0, 0, 1, right? So what happened that this bit got deleted. Then you have this bit that got deleted and these 2 bits are deleted, right? So all the other bits are present, so with probability P. So, and this subsequence, this is called a trace of the original sequence. I will tell you why the name trace. This is completely unintuitive why this would be called a trace, but I will tell you the source of that name. Okay, so what happens in the trace reconstruction problem? You assume that you have IID copies of the traces. So the same binary sequence have been passed to the deletion channel multiple times independently, and you have multiple traces. For example, you see this can be another trace, right, of the same sequence. One other trace can be 1, 0, 0, 1, 0, right? So these are all 3 different IID traces. And the task is to, given this number of traces, figure out what the original binary sequence is. Okay, so recover this vector just by looking at the traces. When you know that all these traces are generated by IID deletions and the traces themselves are independent. Now, the reason this is called trace reconstruction is because it is motivated by DNA sequence reconstruction. And in the biology literature, all of these subsequences of DNA sequences were being called traces. Right, so that's why it is called trace reconstruction. This has nothing to do with the mathematical notion of trace.
Arya, this is Prakash. Hi.
Yes.
The locations of the deletions can vary, right? From
yes, these are just IID deletions. So they can be in different places, in different sequences. So you can think of another application in some packet drop networks where you send a binary string or say any like some query string, and each bit is each ALF packet or each whatever query bits, query integers are actually coordinates are being dropped, IID. You receive something, now you request it again, and you receive another copy over the same deletion channel. And now the question is how many such traces you need to reconstruct back the original sequence. Okay. So, okay, sorry. I don't know. So I think there can be only, yeah, okay. So now how many traces you need to reconstruct X? Suppose X is the one that was being sent. Now you, like with certainty, you can never be able to reconstruct X because these are IID deletion channels. It might happen that with some probability, every bit is being deleted in all the traces that you have, you are requesting, right? So it has to, you need to reconstruct with high probability. So probability 1 minus little o of 1, where this term, little o of 1 term, it is going to go to 0 with n, or m, where n is the length of the sequence, and so X belongs to, and m is probably the number of traces, right? So in particular, you want how many traces do you need? So you want basically this m as a function of n, such that this happens with probability 1 minus little o. So this is little o 1. Okay, so this is going to, this term is going to go to 0 with n. So this is the problem. And now the results in trace reconstruction can also be of two flavors. So first of all, let me give a little bit historical context of this. So this problem can be defined for other channels as well, right? It can be defined for binary symmetric channel. It can be defined for binary erasure channel, where you basically just say you start with a binary sequence, binary vector, pass it through a binary erasure channel, say, got an output. Now, how many such, like now you do this again and get another output, how many such sequences at the output, like how many such passings through binary erasure channel you would need to reconstruct back the original sequence? And the problem there is pretty easy, both for binary erasure channel and for binary symmetric channel. You can see that, as a matter of fact, only logarithmic number of sequences, or maybe polylogarithmic number of sequences are sufficient. For the case of binary erasure channel, you just want, for each coordinate, you just want one sequence where it is one sequence at the output of the channel where the bit is not erased, right? So there is perfect synchronization, so you'll be able to recover it. For the binary symmetric channel, the natural algorithm would be to take a coordinate-wise majority, and that then it is easy as well. So all these have been introduced in a paper by Levenstein, okay, except for the case of deletion channel. So for deletion channel, Levenstein looked at the combinatorial problem. So he basically said that, okay, I have subsequences, which, so here all the subsequences that we are receiving as traces are random. So Levenstein said I have subsequences that are received from a sequence by deleting at most d bits. Now recover the original sequence, and that problem is quite different than this one, exactly like many coding theoretic problems are, or error correcting code problems for adversarial channels are different from like their Shannon theoretic counterparts. So that problem is quite different. This, in this form, the way I'm presenting it, it is being first introduced in a paper by Batu et al. So Batu, Kannan, and Andrew McGregor was one of the authors who is a co-author of mine in this work as well, the work that I'm going to present. So in 2004, right? And the result of trace reconstruction can be of, again, different flavor. So first is worst case. So this worst case refers to the fact that you don't know anything about X. Someone has just arbitrarily chosen some X, so you don't have a prior on it, and you have received just this IID traces. You want to reconstruct back X. And it can also be, so it's called average case, but what does average case here refer to? Average case refer to the case when you have a prior on X. You know that X is IID Bernoulli half. Okay, and the answers for these two problems are quite different. So by answer, I mean the answer to the question that how many traces you need to reconstruct X. And not only they are quite different, there is like a huge gap. They're drastically different. And even within themselves, like there can be upper and lower bound on the number. So the exact number is not known for both of these cases. And there is an exponential gap in the upper and lower bounds. Okay, so it turns out that the deletion channel is, as we know, the deletion channel, or many of us know, the deletion channel is notorious in information theory in terms of calculating capacities and so on. Here, this problem is incredibly more difficult than the problems of the binary erasure channel or binary symmetric channel, and the answers are also drastically different. As I mentioned, even for the worst case for binary erasure channel or binary symmetric channel, you basically just need logarithmic number of traces to reconstruct. But in this case, for the worst case, you need the best known upper bound, and this is basically 7 days ago. So there was a paper that came out just 7 days ago. After this talk, I agreed to give this talk. So this is the result. This is exponential order of, so there is a, because there are polylog terms, n to the power 1/5. This is the best known upper bound. This is by Chase, Zachary Chase, so 2020. The lower bound is also by Chase in a different paper. I think it appeared in arXiv late 2020, but it is published this year. So it's again from 2020. So the lower bound is order of n to the power, let me just see, it is 3/2, again by Chase. Okay, so you see these two quantities. So one is just a polynomial over here, and the other one is exponential. And before last week, the best result was, so I'm just writing, before last week, the best upper bound was exponential order of n to the power 1/3. This was from 2017 by Nazarov and Perez, and also in a different paper by the et al. So I'm going to discuss the technique of Nazarov and Perez because that technique has been refined later on to derive this very current result as well. If we have time, we will see we will briefly discuss what is the difference between this and this. How do we get to this? Okay, so this is the status. So for the average case, so we are going to talk about this worst case reconstruction. So this part over here. We are not going to talk about the average case. So average case is significantly easier. So all this exponential bound, so this actually, I mean, what is surprising in that is that in average case, you can do it with a sublinear number of traces. So the best known upper bound is exponential O tilde of log n to the power, I forgot, maybe 1/3. Yeah, something like this. So exponential log n is linear. So this is log n to the power which is less than 1. So this is actually sublinear number of traces. But the lower bound is order of some polylog n. Right? So even there is a huge gap. And again, if I have a little time, I will, at the end, I can discuss why average case trace reconstruction. Oh, let me just tell it anyway. So in average case trace reconstruction, you can actually naturally see some anchor sequences or marker sequences because these are randomly generated, right? So there you will see some pattern of subsequences that are not likely to repeat itself many times, right? So if you see those sequences in traces, you can sort of align the traces. Whereas in the adversarial case, or the worst case, it is not really what you get to see. Okay, so if we have time, we'll come back to it later. So far, is there any question in terms of results? Now we are going to go to the technicality of how do we prove these results. Okay, so let me move on. So this result of Nazarov and Perez and de et al., which is exponential, this many traces suffices, right? This many traces suffices. So this comes from something called a mean-based algorithm. So what is I will come to what is a mean-based algorithm. So let's see what is a natural way to solve this trace reconstruction problem. The way they derive this result is via some complex analytic method. We'll see how this complex analytic method again comes up naturally. So suppose you have this vector x, which is say x1 up to xn. So this was the vector that is sent through a deletion channel. And then at the output, you receive this trace. When potentially this can again be n bits long. So, but in reality, this is a deletion p. So you know that most likely the length of this sequence is some n prime, which is approximately 1 minus p times n. But what we are going to, I'm still writing it as a n bit long sequence. And what I am going to do is I'm just going to add like pad zeros at the end of the trace to make it n bit, just for the ease of exposition. Okay. So this is actually a random vector, right? This is a random vector. This is a deterministic vector. This is something that we don't know, but we want to recover this. Goes through this deletion, you get this random vector. Now, think of this. So what would be one natural way to look at this? So suppose there are two candidates, x and x prime, that are not equal. If somehow you can show that expectation of when they're passed through the deletion channel, they become this random vectors, and I'm going to write those random vectors with the tildes. So there is a reason like why I'm doing this instead of writing things as capital letters. I think that, so expectation of x tilde is just the average value of the trace when the original sequence was x. Okay. So if we can, so this is expectation of a random vector n bit long. Now, for any two x and x prime, if I can show that the L1 distance between them is lower bounded by something big, then actually I will be able to separate out the traces exactly by a logic that I have given you before. Okay, so all the algorithms that actually uses this coordinate-wise averaging or this expectations are called mean-based algorithms. So this is what is called a mean-based algorithm, where we look at just expected values or the coordinate-wise averages of the traces. Okay, so that's what, and among the mean-based algorithms, it turns out that this result is optimal. So the new result that we have just 7 days ago is not a mean-based algorithm. We'll talk about it later. Okay, so far so good. So if we can show that this is lower bounded for any two candidate sequences, their average traces are far apart, then what we can do is we can take a number of samples, find out the coordinate-wise average, go over all possible all possible sequences, right? In 0, 1 to the power n. So there are 2 to the power n of them, and find out which one is the closest to the average in terms of L1 distance. And we are going to output that. Again, we are not worried about computational complexity because our sample complexity already is exponential, right? So there is no way you can do it efficiently with this many samples. But for that minimum distance search, you can write a linear program and make it polynomial in exponential n to the power 1/3, which basically is exponential n to the power 1/3, right? So you can always do something like that. So that's what is a mean-based algorithm. So our first task is going to be is to show that we are going to prove this theorem that this many traces suffice. We are going to first show that for some x not equals to x prime, this L1 distance over here between their corresponding average traces is going to be big. Okay, any question here? If not, I will just try to do this calculation. So we want to find, I'm just writing this coordinate wise, I greater than equal to 0. You know, I can go from 1 to n, but let me just write 0 to n minus 1, say. It doesn't really matter. So you have EXI. So this is the expected value of the ith coordinate. X prime tilde. So this is what you want to find, right? So this is the L1 distance between two average traces. So the way we arrive at this, we do this calculation. This is actually a very complicated thing to calculate. It's not that there is some other barrier. If you just try to write out these probabilities and then try to calculate, it's very hard to get something which is manageable. So, you know, we have this single letter characterizations in information theory or in computer science. Many times we say order of n to the power something. One of the main challenges of calculating, we know that if we can do a very complicated calculation, there is an expression, but we want to still simplify this expression. So what I'm going to do is to get a nice simplification for this quantity, and for that I'm going to use complex-analytic technique. Okay. So what we find.
Hi, this is Prakash. It relates to a question I asked earlier, because all these sequences that come out, before you pad them, have different lengths. So you know the number of deletions. Now, where is that information being used in the algorithm? In other words, you know something about the number of deletions, the way the deletion intensity works. When it's being used in the algorithm that you mentioned, you find this expectation difference, the L1 norm, and then you work with it.
Right. So in the mean-based algorithm, that information for individual samples, when you get one particular trace, you obviously know exactly how many bits are being deleted. So when you use this mean-based algorithm, you don't use that information explicitly anymore. One of the reasons is you know that with high probability, the number of deletions is approximately Pn. That's what you are going to see. So unless that it deviates it from that number significantly, you are not going to use it. You will see that when I'm calculating this, I'm actually using the probabilities, and there will be some concentration inequalities that comes up. So that sort of subsumes that information. So although in the algorithm, we are not using this explicitly, unless there is like significant deviation from the mean, this information is not going to be useful. It's not going to add extra help. Right, and again, like mean-based algorithms are not the optimal algorithm. As I said, I mean, up till 10 days ago, I wouldn't be able to give you a counter example of a non-mean-based algorithm that is performing better than this, but now there is one. Although I have not internalized that paper, but seems correct and everything. So there is, you can have non-mean-based algorithm But the nice thing about mean-based algorithm, as we will see later on, is that they connect really nicely to mixtures. Okay, so and the connection to mixtures is a nice thing in this entire story.
All right. Thanks.
Okay, so let's just try to do this calculation. So instead of finding this, I'm going to find the following quantity. So expectation of xi tilde minus expectation of xi prime tilde. So we were to find this, but instead I'm going to find this times some sort of a generating sequence over here, right? So why so see that this W here is a complex number. W here is a complex number. Now, if somehow I can make the absolute value of W to be 1, then whatever I have wrote down is exactly what I want to find. So I will do the calculation and I will try to keep the value of W as close to 1 as possible later on. So I'm calculating this, but now just by using triangle inequality, my first step is going to be this. This is greater than equal. So I can just take the absolute values outside of the summation, right? X tilde I, W to the power I, minus summation xi prime tilde W to the power I. Okay, so far so good. So now I have this quantity, like I have these two quantities, one over here, one over here. They're both looking quite similar. So I'm just going to calculate one of them. So I'm going to calculate out I greater than equal to 0 expectation of xi tilde W to the power I, right? So now this one is not very difficult to calculate since I have this W to the power I over here. Why is this not very difficult to calculate? Because I know the probability distribution of xi, so I'll be very easily able to find what is expectation of xi tilde. So I know the probability distribution of xi tilde, right? Because I know that xi tilde is actually xj. So j has to be, so actually I don't need a second brace over here. For j greater than equal to I. So you see, this is, you have a subsequence. So, and this was the original sequence. Now you have a subsequence. So suppose this is ith bit. Since this is a deletion channel and you are looking at ith bit over here, right? So it cannot be the case that the ith bit is coming from somewhere in this side, right? So it can only come from somewhere which is greater than I, right? So this is going to be xj is up to the jth bit, exactly j minus I bits are deleted or I bits are retained. This happens with probability j choose j minus I, so this many bits are being deleted. Then p was the deletion probability, j minus I, 1 minus p to the power I, right? So this is the exact probability distribution. So what is expectation of xi? Expectation of xi tilde, this is simply the sum of j over j greater than equals to I, j choose I, p to the power j minus I, 1 minus p to the power I, xj, right? So this is a closed form, not closed form, but this is the expression for expectation of xi tilde. Again, if you have any question, you can just ask me. So it means, so if the jth bit comes out, happens to be the ith bit in the traces, then up to the jth bit in the original sequence, exactly j minus I bits have to be deleted, right? So j choose j minus I is actually j choose I. So that's how I wrote it down. So now look at this summation, right? this summation now becomes a double summation, right? Sum over I greater than equal to 0, then summation of j greater than equal to I. Then you have j choose I, p to the power, sorry, j minus I, 1 minus p to the power I, w to the power I, and xj. Okay, so whenever we have something like this, what we do is we change the order of the summations, right? So there are two summations. So I is greater than equal to 0 and j is greater than equal to I. So when we change the order and make j greater than equal to 0, then I can be at most j, right? So that's changing the order of the summation, and xj depend only on j. So I'm taking xj out. What we have inside is a very nice binomial sum. J choose I, 1 minus p to the power I, p to the power, sorry, j minus I, w to the power I. Okay, so I can, so this is 1 minus p to the power I and this is w to the power I. I can combine them, and this entire thing is basically a binomial sum. So this is sum over j greater than equal to 0 xj. Then I have 1 minus p times w plus p whole to the power j. It's just a calculation, but it turns out to be this. Okay, so now let's just go back and see where we were. So we were trying to find this quantity over here. Turns out to be the difference between these two quantities over here, and we have calculated this quantity, right? So we are just going to now go back to this. So we just write, therefore, sum over I greater than equal to 0 xi tilde minus xi prime tilde w to the power I. So this is what we have. This is actually, this was the direction of the inequality, and we have found the individual terms. So it turns out this is greater than equal to sum over j greater than equal to 0 xj minus xj prime 1 minus p times w plus p times p to the power j. So far this is pretty elementary, right? So what we did is that somehow we converted, like so we had the traces, and we were looking at the difference between mean traces. We converted it when we are taking expectation, because of we are looking at the difference between mean traces. We just converted up to a change in variables over here to something that depends on the difference between the original sequence, right? So this is actually the original sequence xj. So the tildes are gone, and that is to be expected because we had this this expectation. So this has to be something deterministic and has to depend on xj, the original x, and that's what we found. Okay, so now we can think of this xj. What we have on the right hand side is actually absolute value of a complex polynomial, right? So we have xj minus xj prime. So let's call this aj, right? So then this thing, and then let's also do this substitution. Z is 1 minus p w plus p. So this equal to, therefore, sum over aj z to the power j, which we can write again as a complex polynomial az, right? This absolute value of a complex polynomial. So somehow, and we want this as a lower bound on something, so we somehow have to show that the absolute value of a complex polynomial is lower bounded. But we know something more about this complex polynomial. We know that these aj's can take only 3 values, -1, 0, and 1. Okay. So such polynomials are called little root polynomials. So why are they called little root polynomials? Because little root basically studied in a series of papers properties of polynomials, properties of complex polynomials, whose coefficients are coming from some restricted set, right? And this is actually a very particular little root polynomial, a very particular restricted set where it can take only three values, -1, 0, and 1. And now we are going to use a lemma by Borwin and Italy, and I will give you an 1997. So that basically just calculates the maximum over a small arc, the value of a little root, the maximum value of a little root absolute value, maximum absolute value of a little root polynomial over a small arc. So this B lemma, this basically just states that maximum, and I'm going to explain what does this mean, maximum of e to the power I theta, so it's a complex polynomial, when theta is in a small arc. And we need this small arc because we somehow also have a W over here on the left hand side. So we need that the fact that the arc is small to control that. We will see shortly. So they have shown this. So if you have a little root polynomial, exactly the polynomial that I have defined above, then this is going to happen, right? So what does this mean? If you look at the complex plane, so this is the unit circle, right? This is the unit circle. And now you are taking a small arc and evaluating the value of the polynomial over that arc. So this is saying that that value cannot be uniformly small. And we sort of have some intuition to like, okay, so this was proved in 1997. This is not proved in 1930s so or 1940s when we will expect a lot of this kind of things were being proved, right? So it requires some technicality, but here is the thing, what happens when L is 1, right? So then you are basically looking at the maximum of absolute value of a complex polynomial over the entire circle, over the entire unit circle. Now you can, and then this is really trivial that this has to be a constant. Why? Because from Parseval's theorem, we know that what we are doing here is just a Fourier transform type of thing, right? So we're just doing a Fourier transform. So the energy of the, like when you are integrating over the entire arc, the energy is going to remain the same. Of energy is the square value of the vector that you are taking transform of is going to remain the same. Okay, so then it is, and what is special over here is that it is saying that even if your polynomial is special, like this little root polynomials, then you can take this integration, you can integrate this function over a very small arc, and it's still going to be something non-trivial. Like you are not going to get something, so this is not uniformly close to 0. So its maximum is going to be bounded away by 0. And now the smaller your arc is, the smoother this transformation is. So somehow the fact that the coefficients are coming from, coefficients are discrete, they can take only these 3 values in the original polynomial. When you take it to the transform domain, there is this kind of smoothness property that shows up. So it's like this, like if you look at any small frequency band, it's not going to be uniformly 0 or like very close to 0 in that. It will have a value which is away from 0. So in the interest of time, since I'm in the top of the hour, so let me just proceed with the proof and take this as a lemma. Later on, if we get time, like to improve on this lemma, definitely, like as we go to the story of mixture, we want to go inside of the proof of this theorem and change things. Okay, but that's probably out of the scope today anyway. So let's just use this thing as a lemma. So if you use this as a lemma, then what we have is this thing over here, using this lemma, this is bounded by e to the power minus CL when z is absolute value of z is less than equal to something, right? So it's not absolute value of z, it's going to be absolute value of theta. Z is e to the power I theta. So absolute value of theta is bounded by pi over L. And you know that, how is it connected? W plus 1 minus P plus P. So there exists some theta that has their absolute value bounded by this. So you know, in this identity over here on the right hand side, I can substitute with any value of theta, which means I can substitute with any value of z, and that is going to give me a valid lower bound. I have to substitute the corresponding value of w over here, right? And I know that over this small arc, it's lower bounded by this. So I'm taking the value of theta to be upper bounded by pi over L. So there exists some theta that has this property for which this will happen. And this is related to W according to this. And now we basically know that, so this also tells us that W is equal to e to the power I theta minus P divided by 1 minus P, right? So this is what I have. Okay, so I can go to a new slide. Maybe let me just go to a new one. I can come back to it. So this is what I have. Now I just have to do some trigonometric manipulation, right? Because I have to find out the absolute value of W, because that's what is on the left hand side. And I know that W is related to theta with this, and theta is less than this. So I'm just going to use this and do some trigonometric manipulation. So this was my W, cos theta plus I sine theta minus P divided by 1 minus P, right? So, and I just want to find out absolute value of W. Okay, so I know that I can just do this with some trigonometric manipulation. So it turns out that this absolute value, so I can do this I know is cos theta minus P divided by 1 minus P square plus sine theta divided by 1 minus P square, right? I can write this thing out again in the interest of time. Since I want to move to some more interesting and intuitive parts, I don't want to spend a lot of time here. You can show that this is upper bounded by some exponential, some constant, which is particularly pi square divided by 1 minus P square by L square when theta is less than pi over L. So when this happens, this is bound to happen. Okay, so now I can go back. So this was my left hand side. I'm just going to plug in that value of W, so whatever is the maximum value here, I'm going to plug in that thing. So what I will get, is sum over I greater than equal to 0 expectation of xi tilde minus expectation of xi prime tilde. This is greater than equal to exponential. I have minus CL from the lower bound, and then for W I will have minus n over, again, some other constant, and C prime divided by L square. And so to get the best possible bound, I will do just a minimum of L plus n over L square, which is this term over here. And turns out the term L that minimizes this or maximizes the right hand side is actually order of n to the power 1/3. So I have shown that the mean traces, sorry, there will be no I anymore, x tilde minus expectation of x prime tilde. So this L1 distance is exponential minus order of n to the power 1/3. I mean, I shouldn't really write in the sense like Grigor, I shouldn't write order over here, some constant time n to the power 1/3. Okay, so for any true traces, this is going to happen, right? Now again, we can actually, so if that happens, so you see there are two vectors that are some L1 distance apart. These are mean vectors. Now if you get samples, right, and you know that the means are separated, then you will be able to tell whether it is coming from x or x prime, right? So from the samples, and how many samples do you need? You can actually calculate that using Charnock bound. Does that make sense? So you have one mean over here, one mean, another mean over here. So how many and there is some gap you have proved. So now you basically got a bunch of samples which are traces. So trace 1, trace 2, and so on. You can just take the empirical mean of these things, and you can test whether it is coming from here or here just by using something like Charnock bound. So there will be, if it is coming from here under that hypothesis, this should be concentrated around this. So the probability that this will cross this halfway mark and go to this is small. So that's again a calculation like this trigonometric calculation that I'm not going to perform over here. Okay, but now this is giving you a hint why trace reconstruction, not completely, but how is it related to mixtures? So is that clear? So if we use that, it will end up being that the number of samples you need is actually exponential. So there will be some logarithmic terms, but exponential O tilde of n to the power 1/3. Right. So the probability of error is going to be something like if you use m samples, then the probability of error that you make between any two is going to be exponential minus some m over n squared exponential n to the power minus n to the power. Right, and then you can take a union bound over all possible pairs, and you just have a polynomial. So that's not going, this is actually a super exponential decay in probability. So that's going to actually like subdue that exponential union bound, and you will see that basically this many samples are going to suffice. Okay. So that's the story of trace reconstruction. That's the method of Nazarov and Perez. So let's now see how this is going to be related to mixtures. Okay, are you with me so far? Okay, so now one of the ways, there can be multiple ways to relate this thing to mixture. One of the ways that I found it pretty natural is that suppose I have some extra information. I have the information that the binary vector that we started with, binary vector x, has k ones. So suppose this is something that is given to me. So it has a sparsity k, or I'm basically want to do sparse trace reconstruction. Now I'm asking the same question. So I'm going to parameterize trace reconstruction with the number of ones in the trace. Okay, and I'm asking the question that how many traces do we need? How do I use this information that this has k ones? So I'm showing you another way, and now this is going to be more informed to this information. So if you just try to blindly use the technique that I have used, it's not apparent how am I going to use this information that it has k1s, but here is another alternative way to look at this. So suppose Ri, this is the number of ones before the ith 0 in X. So I'm having trouble writing X with this. Okay, so Ri is number, can you, okay, so Ri is the number of ones before the ith 0 in X. Sorry about, just open the door. Now, this Ri's, they uniquely define X. If you give me all the Ri's, the number of ones before the ith 0 in X, they uniquely define X. How is that? Because suppose my sequence is 1 1 1 0 1 0 0. So in that case, what is R1? R1 is 3, R2 is 4, R3 is again 4, right? So this is number of ones. Number of ones before the first 0 is 3, number of 1 before the second 0 is 4, number of 1 before the third 0 is 4. So if someone gives you R1, R2 and R3 and basically says that's it, then first of all you know that there are 3 zeros and you can just basically place the ones in between them accordingly so that you can uniquely reconstruct the vector. So reconstructing a binary vector is equivalent to reconstructing these numbers, the numbers which are number of ones before the ith 0. Now what we do when we go via this mean based algorithm, so this is one way to look at it. So suppose I have a trace x tilde. So what I'm going to do is to pick a random 0 in the trace. Okay. So, and I'm going to count what is the number of ones before it. So say the answer is R. So I randomly pick a 0 from a trace and ask count what is the number of ones before it. So suppose that is R. So now R is a random variable. Can you tell me how this random variable R is distributed? So how is R distributed? So if I pick the random 0 from the trace, if this random 0 were the first 0, you see, so a random 0 in the trace is actually, it can be a random 0 coming from a random 0. So it has a uniform prior of being a random 0 of the original sequence as well, right? So if I pick a random 0, if that were the first 0, then the number of ones before it is simply binomial R1 1 minus P. So let's say Q is 1 minus P. So this is binomial RQ, R1Q, right? So if the 0 is the first 0, if 0 is the second 0, then this is binomial R2Q, and so on. If it is the third 0, it is binomial R3Q, right? So this R, this random variable R, which is the number of ones in a trace before a randomly picked up 0, this is a random variable distributed according to a mixture of binomials. Is this clear? Okay, so when I'm basically trying to do trace reconstruction, what I'm trying to do is to learn this mixture of binomials. So all the calculations I did before is actually learning this mixture of binomials. So we just found out actually, but we can do this again to specifically see how this happens. So we are trying to learn a mixture of binomials. In particular, we want to learn the parameters, right? So if we just see the previous slide, so we want to find out all these RIs over here, all these RIs, right? Because all these RIs are going to uniquely reconstruct the vector X. So what we end up having to do is to learn a mixture of binomials. But this mixture has, so one other point is that all the RIs over here, so this mixture doesn't have to be uniform, right? Because as we have seen that all the RIs here are not necessarily different, they can be same. And if they are same, then the weight of a particular binomial is actually increasing. So since here R2 and R3 are same, instead of being 1 over n minus k3, 1 over 3 here, so they are going to get a weight of 2 over 3, right? So in this case, I will have, for this sequence over here, I'll have two binomials. So one is 1 over 3 binomial 3q, q is the retention probability, plus 2 over 3 binomial 4q. So the only thing is that they are integer multiple of 1 over n minus k, integer multiple of 1 over 3, but they can be non-uniform. Okay, so we are learning a mixture of binomials. So therefore we have two distribution. One is, so suppose these are two candidate traces, and therefore we might get two candidate binomial distribution. Binomial AIQ, and F prime is sum over beta j, they're going from 1 to some d prime maybe. So potentially this d prime, they are all d comma d prime can be unequal, they are less than n minus k. That's what we know. So beta j binomial some b j q. Now the coefficients, the parameters a j b j, that must come from 0 to k, and this alpha j, beta j, they are integer multiple of, say, gamma, where gamma is right. And now what we actually did before is to just find out the total variation distance between these two candidate binomial mixtures, right? And that you can see, we can basically use the same sort of principles. So suppose AI, capital AI, is the atom of the first distribution. This is the probability over F that you saw I, and BI is the probability over F prime that you saw I. Then the total variation distance, or the L1 distance, is simply is half, but we can neglect half later on. So this is simply AI minus BI.
Sorry, I missed that. Could you say it again, please?
Okay, so now I just have a sum exactly like before, and what I'm going to do is to, instead of finding this sum, I will just try to take a generator function of that. So AI minus BI W to the power I, right? And now I separate out the sum. I have something like AI W to the power I going greater than equal to 0. And this, I know how AI is distributed. This is coming from a mixture of binomials, right? So I can have AI written out as j greater than equal to 0, alpha j, aj choose I, q to the power I, 1 minus q to the power aj minus I. Now again, I can interchange the order of these two summation, and in the inside I will have a binomial sum. It turns out that this is going to give me, j is going to come outside. So this is going to be a summation over j. I will have some alpha j qw plus 1 minus q to the power aj. So all in all, this thing, summation of ai minus bi w to the power I, this is going to be lower bounded by, again, a complex polynomial where z is going to be qw plus 1 minus q, and gz is going to be sum over j greater than equal to 0, alpha j z to the power aj minus beta j z to the power bj, right? So the degree of the complex polynomial is going to be maximum of aj and bj for all j, and we know that since the number the aj bj, so this is a degree k polynomial, right? And the coefficients have to be, so both alpha j and beta j are discretized, so the coefficients have to be in, so this is again some sort of little root polynomial, minus 1, so coefficients have to be in the steps of gamma. Right? So this is another little root type polynomial. And you can use the same complex analytic lemma to show that eventually that the total number of traces required in this case is exponential O tilde of k to the power 1/3. So we did sparse trace reconstruction, and we saw that if we have information that the original sequence have k ones, then we can use it by converting it to this binomial mixture. But now this gives us more ideas, right? Now we want to see, like, so we can learn mixture of binomials by this complex analytic technique. So the question is, can we learn other distributions? So are you with me so far? Okay, so yes, it turns out, yes, there is a generic formula or generic scheme for learning mixtures. So it doesn't really only work for binomials, it works for other things. So what I'm going to do is to share okay, so what I'm going to do is basically, can I parallelly share the screen as well? Okay, so let me just see if I can.
Yeah, you have to do 2 steps. Share the screen, and then you'll see a little icon on the bottom right, which...
Can you see this general
good.
scheme now? So it is basically, yeah, I think that writing this would take too much time. So now here is the deal. So suppose you want to learn mixture of some parametric family. So this doesn't even have to be mixture, works for any distribution. So what you need to do is to find some family of function that would convert it, like when you do something like a characteristic function, right? So when you find out this quantity, this expectation of x, expectation of that function, assuming that it is coming from some like some f theta, this becomes something like a polynomial in theta. So polynomial in the parameters, because you know we eventually have to have something like this little root polynomials. So you come up with some functions and basically do the following thing. Let me, maybe steps 2 is going to be easier. So you come up with some function gtx, and you, for two candidates, distribution f and f prime, you try to analyze this thing, the difference between the means, right? And this difference between the means, so this is basically just an integration, right? And this, you can just take the substitute with the maximum value of gtx, take it out, and you will get total variation distance, because if you take out gtx, this integration is just the total variation distance. What turns out to be the case that you will, the maximum of this gtx for most distributions of interest, this becomes unbounded unless you bound it over some domain. We'll tell you with an example. So then you just divide this integration into two parts, one over some omega prime and then the rest. So for one part, you take the supremum over gtx, which is hopefully small. And for the rest of the part, you see this is actually, you use some concentration inequality and show that this is actually a tail probability. So this can be neglected. So in particular, when gtx, so what happens in effect is that this is going to give you a lower bound on the total variation distance. And if you choose this gts xy like wisely, then this left hand side over here, that becomes a little root polynomial. So the trick to make it a little root polynomial is to take this gtx so that expectation of gtx becomes a polynomial, a complex polynomial, with the powers or the exponents being the parameters that you are looking for. So this is very easy to do for Gaussians. You can just take gtx. So this is to be e to the power itx. So then this is the characteristic function. Everything works out fine. When it is Poisson distribution, or some other distribution, you can still find the gtx, and now it is 1 plus it to the power x. It turns out that expectation of that is z to the power lambda, which is a polynomial in lambda. So in case of mixtures, it is lambda is going to be a vector because there are multiple lambdas. So it is going to be sum over z to the power lambda i's. Okay. And since this is gtx for Poisson or something, you can also bound the infinity norm of it when you are within some interval. So you can then plug it in over here and get a lower bound on the total variation distance, which is with respect to the little root polynomial. So this thing becomes the little root polynomial, and you can actually find the lower bound on this using the the complex-analytic lemma. So we can extend this. I wanted to show you this table. So we can take variety of families of mixtures for which there were no prior results, and we can use this trick to get the sample complexity bound of learning the parameters of those distributions. Okay. So which is cool, but there is a drawback to this method. So the main drawback is that we have to find something which is a little root polynomial, right? And for that happens when the parameter space is discrete. That sort of naturally happens. So for the mixture of binomials, since n, if we have unknown n, it's very natural n to be an integer. So n has to be an integer. So we get basically the correct number for learning binomial mixtures. However, when it is something else like Gaussian, the parameter space is not discretized. So you don't really have a polynomial when you just, for any two candidates, you do not really have a little root polynomial. So for Gaussian, we can only do this we can use this type of method when we have the extra assumption that the means are sort of discretized. So the means cannot really, we have a mixture of Gaussians, but the means cannot really take arbitrary values. They have to take values up to some discretization. So for example, they can only be multiples of some very small epsilon. Then in the sample complexity, you will have this epsilon come into picture. Does that make sense? So for some cases, or for example, binomial, it's natural. For some cases like Gaussian, it amounts to an extra assumption. So how do we, so this is a drawback, but we have some way to remove that drawback, which is actually our current work right now. I'm not going to go into that, but this little, so all we have to do is to lower bound the absolute value of a complex function, right? So if that complex function happens to be a little root polynomial, there is already existing result that we can use as lemmas. So when it doesn't happen, it doesn't mean that those functions do not have other properties, right? So for mixture of Gaussians, there are other properties we could use to lower bound this absolute value of the complex function. And we got some new results recently that it is not written out, but we are pushing this method to see, to get basically optimal results for mixture of Gaussians and so on. So I hope, I think I have covered a lot, and I don't want to keep you guys beyond this, this timeline, which is like it's 1.5 hours exactly. So we did provide a complex analytic framework for learning mixture, which is inspired by the trace reconstruction problem. And I show that the trace reconstruction problem is actually not so different from mixture anyway. So, and this method has strong potential, and we are right now exploring general functions that has this Borwin-Adderley type property, so that you are evaluating it over a small arc. It's not all uniformly small, right? And that is going to lead us to lower bounding total variation distance. And if we have lower bounds on total variation distance between any two candidates, we can tell to distribute with, we can do the testing. We can basically say whether a set of samples coming from one distribution or other, and then we can basically do learning as well, just by going over all possible pairs. Okay, so I wouldn't say any more. Let me just end here. Thank you very much for listening to it for so long.
Thank you, Arya. Is there anybody have any questions?
Yeah, this is Prakash. Hi, Arya. Thank you very much. It was a very nice talk. I had the following question. The one version of estimating mixtures in a distribution is the following. The observed data, let's say, emitted by an IID source, then the empirical distribution is gathered, and then it's we try to approximate it by a mixture of fixed distributions, and the objective is to estimate the mixture parameters. And this is done in the sense of Kullback-Leibler divergence and maybe L1, and there are algorithms for doing that. Now, in your application, the observations are, of course, at the output of the deletion channel. If you change, in your problem, of course, you wish to reconstruct the trace itself, but suppose the trace were generated by an unknown distribution, and you want to estimate that unknown distribution. Does this method extend itself to doing that? That might be an easier problem in some sense, right?
So here is what if I understand this correctly. So instead of, so what do you mean by, so the traces, so you still have a deletion channel and IID deletion, or do you want to change that as well?
Keep it the same way. You have an IID deletion channel, and you have an input sequence that comes from
Right.
Close to the
That's a very interesting question, and there is answers to it. So this is actually the what is also called the population recovery problem in this. So you assume that there is a set. It can be all possible binary vectors. The set can be, and then there is a distribution over this set. And now, according to that distribution, you picked up a vector and you get a trace by passing it through the deletion channel. Now you can get, you basically repeat this thing and get independent samples or independent traces. So it's not necessarily coming from, so the entire process is you generate X according to that distribution. And
I see.
So right, so that's the problem. That's so in that case, actually, this complex analytic method has been used, and the results are actually weaker compared to what we have for one. Like in a special case, it turns out to be whatever I have presented today.
Okay.
So it's not like whether it is making things easy. I'm not sure about that. So the aim is to basically learn that distribution, by the way.
Right, yeah.
So, yeah, in this case, in the very special case, I have a singleton distribution, right? So which is just one vector X. So that part is fixed. So yeah, so you can have the population recovery problem, which is exactly what you said. And in that case, the results are sort of general, but in the special case, they reduce to this. So it's not, I don't think it is making things, so it's still this exponential n to the power something, that type of, I mean, it's probably even more like it reduces to that when you use the special case of a singleton distribution.
I see.
So, and those works are very recent, like in 2019, 20.
I see.
So the population recovery problem is also interesting, is non-trivial even in the case of binary erasure channel.
Okay, I see. All right. Sure.
And there is a paper by Polyansky and Ihong and Yuri basically. So they have results for binary erasure channel and binary symmetric channel. And the deletion channel is just very recent papers, not by them, but by someone else.
Okay. Thank you very much.
Okay.
So Arya, thank you. Let me give a round of applause. Thank you very much. Very interesting talk.